just woken up. So, third lecture.
Hello. So thanks. So this is my third lecture on topological recursion. So I recall what I said yesterday. Yesterday I explained that omega gn in general can be decomposed on the basis of some forms. So we have the basis of form psi a d of z I, which are the coefficients. So they are the residues of b times some power. So they are the coefficients in the expansion of b. They are the coefficients of the Taylor expansion of the two form b near a branch. When one of the variables is near a branch point, the coefficient is the one form in the other variable. So these coefficients are called psi ad. So they are just the coefficient of the Taylor expansion. And for instance, let me write omega 04. It's a certain combination of some psi ad a1 d1 of z1, psi a2 d2 of z2, and so on. I'm just writing that this is a form which I decompose on the basis of forms. It's just so the coefficients here are just the coefficients of the decomposition in that basis. And let me write those coefficients fgn and they depend on the indices of the basis, so a1 d1, a2 d2, and so on. And I also like to put a prefactor 2 to the power of 3g minus 3 plus n. It's convenient. All right, so far I've said nothing. I've just said that I have a form and I decompose it on the basis of forms. Now, what are these coefficients? And also, because the coefficients are obtained by a recursion, necessarily the coefficients will be algebraic combinations, and in fact polynomials, of all the Taylor expansion coefficients that appear in this framework. So basically they can be combinations of the times TAKs, the times TKs. Well, here this is the example where there's only one branch point, so I write TK instead of TAK because there is only one A, and it's A equals 0 in fact in this example. So the coefficients fgn are functions of those TKs, and they are polynomial functions of those TKs. They are also polynomials of the coefficients of the Taylor expansion of B. So the fgn should be universal polynomials, and it's obvious that they are rational polynomials. In fact, if I would not put those 2d plus 1 double factorial, those powers of 2 and so on, I could even make them integer coefficient polynomials. But it's convenient to put the 2d factorial, so in order to recover the intersection numbers. And the intersection numbers are rational numbers. So what I will show you, and this is what this first theorem says here. Let me reduce a little bit. So what this first theorem says, it's the example where the curve, the spectral curve, has only one ramification point, and I put it at 0. You see the projection is z squared, and the ramification point is at z equals 0, this example. And the one form eta, let's take it rather generic, so let's take its Taylor expansion at 0, and the coefficients are called TKs times some combinatorial factor. And let me also take the B, the simplest possible B, just 1 over z1 minus z2 to the square dz1 dz2. Later, I will choose more general B in the next slide. So there will be 3 such theorems. The next slide is the same theorem, but now with B equal this term plus some expansion near 0. And the coefficients are called BKLs. So basically this will be the improvement of the first theorem for that case. The third theorem that I'm going to mention is the case where there are several ramification points. And it means that we have to compute Taylor expansion coefficient at each ramification point for eta, for B, and so on. And you will see the result in a moment. So let me come back to the first theorem. Let me enlarge the interesting part. So you see the result is that the coefficients, so this big bracket is in fact the coefficient that I wrote fgn here. This big bracket is that coefficient. And it is an integral over some mgn bar of some, it involves some psi classes and tau classes. Another way of writing the same coefficient is with psi classes and kappa classes. So let me mention a little bit what they are. And also let me mention something. The coefficients tk's, you can obtain them as the Taylor expansion of eta at 0. There is another way to obtain the same expansion coefficients, and somehow it's by taking the Laplace transform. The Laplace transforms somehow will kill the denominators on the power of 2 here, so it will make directly a series, sum of tku to the minus k. I will show you in a moment how it works. And the times tk's are defined now as the coefficient of the expansion at large u of the Laplace transform. And I also define new times. Let me enlarge because it's hardly possible to read. I also define some other coefficients t hat k's. Basically, the series sum of t hat k's u minus k is the log of the series of 1 plus sum of tk u minus k. So there is it's just a change of variable between the tk's and the t hat k's. The t hat k's are combinations of the tk's, or vice versa, the tk's are combination of the t hat k's. But these are the coefficients that you need for the kappa classes. So let me say more about these two theorems. Okay. So let me say more about these two theorems. I'll give a hint of how to prove them. First of all, let me recall some basic facts about intersection numbers. MGN is the moduli space of surfaces of genus G with n mark points, and labeled mark points. I mean, there is really a numbering of the mark points. MGN is the moduli space of smooth surfaces, but the Dölling-Mumford compactification of MGN bar, is obtained by adding nodal stable surfaces. Nodal stable means that you have surfaces made of several components glued just by a nodal point. And stable means that every component must have strictly negative Euler characteristics. So basically, here you have, for instance, a sphere. This component is a sphere. It has 2 nodal points on 1 mark point. So it's fine. It's like a sphere with 3 mark points. It has Euler characteristic -1. So you would not like to have a sphere with just 1 nodal point or 2 nodal points or 1 mark point. I mean, you don't want that. Okay, this is the compactification of that space, because somehow this corresponds to pinching a cycle. And there is a notion of dual graph associated to this. The dual graph of such a nodal surface means that here you have a component with genus 1 on 2 mark points. It's linked to a sphere with 4 mark points, so 0, 4. And to a sphere with 3 mark points, 0, 3. And there is, so each edge now is a nodal point. And so edges of the dual graph correspond to nodal points, and vertices of the dual graph correspond to the pieces, to the pieces. And also the mark points are always smooth mark points. So there is a cotangent space. It makes a line bundle over MGN bar, the cotangent space of the ith mark point, and you call psi I. It's first Chern class of that cotangent space, and this is a 2 form. It's usual to denote psi I to the power k. It's usual to denote it tau k. This is the Witten's notation, and then it is a 2k form. This one is a 2k form. This one is a 2 form. Okay. Now there is the notion of kappa classes. I started to mention in last time. What is kappa classes? You have a forgetful map. Let me call it pi also. For MGN plus 1 bar to MGN bar, which just means forget the last mark point. And under that forgetful map, the push forward of the psi class of the n+1 mark point, so the one you forget, to the power k+1. So the push forward of that is what you call kappa k, and it's called the Mumford class, and it's a 2K form. Okay. And Arbarello Conalba I don't remember what year. Okay. They made the following theorem. Well, that's basically if you have an integral over mgn bar of well, it's just a theorem saying that mgn plus m psi 1 d1 psi n dn psi n plus 1 k1 plus 1 psi n plus m km plus 1. And so you're going to forget, so now you're going to relate that to some integral over mgn of some classes. And so this is the sum over all sigma permutation of sigma m. Let me get it correct. mgn bar psi 1 d1 psi n dn times the product of kappa classes, product of kappa, while C equals cycles of sigma, of kappa of the kappa, let me call it kappa of C. Well, it's the sum of all the ki's that belong to the cycle C. There is a nice way to write that, but let me just say first that if you want to write something like exponential, let's say exponential tau 3, psi 1 d1, psi 2 d2, just an example. What does it mean? If you want, so what does it mean to write exponentials? Exponentials mean that you should do the Taylor expansion, sum over m, 1 over m factorial, integral over mgn. So here it was mgn. Okay. No, okay, I should not write it this way. Okay. Let me, so the convention is to denote tau d1, tau dn g is the integral over mgn bar of psi 1 to the d1, psi n to the dn. So this is the notation, and also this is 0 if sum of di different from 3g minus 3 plus n. So the convention is that the intersection number is 0 if the dimension is not the correct dimension. So when now I write exponential tau 3, for instance tau 1, tau 2, in genus G, well, we don't write the n. The n is the number of tau factors. It's not necessary to write it. So by definition, this is sum over m, 1 over m factorial, tau 3 to the m, tau 1, tau 2. In genus G. This is by definition. And in that sum, there will be only one value of m for which the dimension will be satisfied. So in fact, it's not really an infinite sum. It's in fact a finite sum. There is only one non-vanishing term in the sum. So in general, exponentials of tau classes are in fact polynomials of tau classes. may look strange, but in fact they are polynomials. And so a nice way to write Arbarello kernel bar is the following. Exponential, so if you take a generating series, minus sum of tk tau k plus 1, and psi1 d1 psi n dn g equals exponential sum of t hat k kappa k psi1 d1 psi n dn. Again, the second line means you should do the Taylor expansion of the exponential, and in fact only a finite number of terms will be non-vanishing. Where the t hat k's are functions of the t k's by as follows. So you make a generating series, sum of t hat k u to the minus k exponential minus that equals sum of tk u minus k 1 plus no, sorry, 1 minus. Okay, and for instance, you have t hat 1 equals t1, and t hat 2 equals, I don't remember it by heart, so t hat 2, so for instance, t hat 2 is t2 plus 1 half of t1 squared. And so on. Okay. So this is what I've used here. So this is what I've used here. I just rewrite this as that, and probably the sign is wrong. Sorry. Okay. And by definition, the TKs are the coefficients obtained by doing a Laplace transform of eta. Let me give you an example of application of this theorem for the following spectral curve. I'm going to take a spectral curve that is not algebraic. It's the sine function. So let me take the example where pi of z equals z squared, and eta of z is it will be sine of 2 pi z times some prefactor that I don't remember better, minus 1 or 4 pi okay, and b of z1 z2 is dz1 dz2 over z1 minus z2 to the square. Okay, let's compute the times t hat k's for that curve. So let's compute the times t hat k. So we have exponential minus sum of t hat k. Sorry. Let me start by doing the Laplace transform. So integral exponential minus u z squared and times this eta of z, and we shall integrate on the real axis. Okay. What is it? So we have integral on the real axis of exponential minus u z squared minus z over 2 pi sine 2 pi z dz. Okay. First we shall, I think, integrate by parts one time and see that it is 1 over, so 4 pi u integral of cos 2 pi z exponential minus u z squared dz and I probably got it wrong. The prefactor. Okay. I don't guarantee the prefactor here. But okay, let me concentrate on the second part, on this integral. This integral is 1/2 of integral of exponential 2 pi I z plus exponential minus 2 pi I z exponential minus u z squared dz. Okay, you complete the square, so it's 1/2 of integral of exponential minus u z minus pi I to the square plus exponential minus u z plus pi I to the square times dz, and multiply by exponential minus u pi square minus u pi square minus 1 over u square. And well, here you just complete, well, basically the first integral now gives you 1 over square root of, well, square root of pi over 2u, something like that. So this will give square root of pi over 2u, no, square root of pi over u, plus the second is square root of pi over u, so basically you get minus 1 over u pi square. Okay? If you look at the definition, I have to multiply by 2u to the 3/2, divide by square root of pi, and so on. And in the end, what you will see is that, for example, exponential minus sum of t hat k u minus k will be just exponential minus 1 over u pi square. Which means that basically t hat 1 equals pi square, and all the other t hat k's are 0. So in the end, what it tells you is that this exponential minus exponential sum of t hat k kappa k is just exponential pi square kappa 1. And it is a famous result by Volpert. And Volpert says that 2 pi square kappa 1 is the Weil-Peterson form. It's a 2 form, and it's the Weil-Peterson form. You can read probably. So 2 pi square kappa 1 is the Weil-Peterson form. So in other words, this theorem applied to that curve says that the topological recursion, the forms generated by topological recursion are the Weil-Peterson volumes. So another way to state this theorem is that the Weil-Peterson volumes satisfy the topological recursion for that curve. And if you write the recursion in details, you will recognize Mirzaghani's recursion. So in other words, this theorem is a proof of Mirzaghani's recursion. And the most difficult part of the proof is this computation, if you apply the theorem. So first it means you have to know the theorem. How can you prove this theorem? Well, first, let me say a few words of how to prove the theorem. The theorem is true for when all the tk's are 0. So when you just have z squared dz, so if you just have 1 here, then all the t hat k's or tk's are 0. So basically it's just the intersection numbers. And so what you have to prove is that for the curve where eta of z equals z squared dz, you have to prove that what you get are indeed the intersection numbers. And there are many ways to prove it. I'm not going to do it, but just take it as a fact. For the simplest curve, the airy curve, you get the intersection numbers. Now, what happens when you turn on the T case? Well, there is a theorem I mentioned to you the other day that topological recursion satisfies a property which I call special geometry. And one way to write it is that, so a way to write, so basically what it means is that their derivatives are integrals. D over dtk of these coefficients fgn of a1, d1, an, dn is equal to fgn plus 1 of a1, d1, sorry, for the moment I have no a equals 0 here. You have just have a equals 0. So let me call the coefficients d1, dn. So for the case where there is only one branch point, this is fgn plus 1 of d1, dn and k plus 1. Well, probably there is a combinatorial prefactor like minus 1 off on 2k plus 1 or something like that. Okay, due to our normalizations, but this is a property of topological recursion which you can prove by recursion. And it's true for all spectral curves. And if you think about what it means precisely, so basically it's a first order linear differential equation, and the solution is an exponential. The solution to that is clearly that. And the next line is obtained by Arbarello-Cornalba. So this is just a sketch of a proof. And so this property, you have to believe me, but it can be proved by recursion from the topological recursion. And it's a general property of topological recursion. Now let me move to a more complicated case, which is now turn on the Taylor expansion of B. So now we don't take any more B equals 1 over Z1 minus Z2 to a square, but we add a full Taylor expansion to it. Now the Xids are no longer also, before the Xids were just exactly this rational fraction. Now they have also extra terms, the Xids, because they are the residues of B at, they are the Taylor expansion coefficient of B, so they depend on B, that's normal. And now what is the result? So you have to study now how the coefficients Fgn depend on B, on the coefficients B. Let me just write what I was writing yesterday, that for instance, let's write omega 2, 1. Okay, omega 1, 2 of Z1, Z2. According to the diagram that I was drawing yesterday, it was this graph. Plus, there was 2 times this graph, plus 2 times the graph Z1 so remember what these graphs mean. So here you have, so let's give a name to variable z and z prime that are integrated at the vertex. So this graph means k of z1 z, k of z z prime, b of z z2, and b of z prime, sorry, sigma I of z, so it's minus z here, b of z prime and minus z prime. And you have to take a residue when z goes to 0 and a residue when z prime goes to 0. And you first take the residue in z prime, then the residue in z. So this is the value of that graph. Now, where do the coefficients b, k, l appear in that formula? Well, they appear here, here, and in K, remember that K contains a numerator and the denominator. And B appears in the numerator, and eta appears in the denominator. So B appears in the numerator of K. So in fact, the coefficients BKL appear in 4 places in that formula. They appear here in the numerator, here in the numerator, here in the numerator, here in the numerator. So which means that the result of this residue will be typically a polynomial of degree 4 in the BKLs. So this will be a polynomial of degree 4, or of degree at most 4 in the coefficients BKLs. Well, in fact, the B that is associated to Z2, when you do the Taylor expansion, you will not really use the BKLs. Instead, you will use the side Ds. So in fact, you can even see that this B will not produce some coefficients BKLs. So the degree is at most 3. And 3 is the number of edges that you could cut, and also, sorry, this one also, because when you expand, Z1 is not near branch point, so when you expand, this one is also, you expand in terms of its size. So in fact, the degree is really 2. And 2 is the number of edges that you could cut in that graph. So basically that one or that one. And here in that graph, it could be that one or that one. And okay, what I'm saying in the end is that you have a certain polynomial of degree 2, and the coefficients of that polynomial are associated to graphs. They can be computed by graphs, and it can be shown that it can be computed by Feynman graphs. And in the end, because it's Feynman graph, it's always something exponential quadratic. It's just a property of combinatorics. I will not go in deeper details, but what I need to explain now is the notation which I write here. What time is it? Okay. What I need to explain is this notation here. And let me come back to my MGN. Okay. Erase my MGN. Let me come back to MGN. To MGN bar. MGN bar, sorry, MGN is not compact because it has a boundary. So let's take, for instance, M12. M12. So it's the space of all Riemann surfaces of genus 1 with 2 marked points. So it's genus 1 with 2 marked points. Let's say 1 and 2. Okay, what is the boundary? The boundary is obtained when you pinch a cycle. So for instance, you could pinch that cycle, and so the boundary terms, so let me say that MDM12, the boundary are, okay, you can pitch 1 cycle, then you can pitch 2 cycles, and so on. And so let's call it the dimension 1 boundary, D1 M12, is when you have pinched exactly 1 cycle. So one possibility is to pinch that cycle, so you will have a sphere. This will become a nodal point. Okay, so this is one possibility. And the other possibility is yes. The other possibility would be, so there are 2 boundary divisors. The other possibility would be you have a sphere with, yes, something like that here. Okay. These are the 2 nodal stable surfaces at the boundary. So you have 2 on delta here in this notation. Delta means the sum of all boundary divisors. So there are 2 values for delta here in that case for M12. And now I will identify this boundary as, so you see it's an M04 here. So if I open somehow I split the mark points, and here also I will it's related to the dual graph I was mentioning before. So basically you have as many, you have exactly a one-to-one correspondence between boundaries on the dual graphs, the degeneration graphs that I was writing before. And now, so it means you have a map L from the M12 into, so here it will be M04, and plus, and here it will be M03 times, times M11. Okay. Now in M04 you have those two mark points, and let's pull back the psi classes of the two mark points to M12. So what I will call L. So we call this one delta 1 and this one delta 2. L delta 1 of psi k, psi prime. So let's call these points P and P prime. Psi k, yes. Okay. Will be the pull. So let's consider the pullback by this map of these pairs of psi classes. Sorry, psi p to the power k and psi p prime to the power k prime. Okay. So now this is a class in M. This is a cohomology class in M12. No, sorry. Okay. Well. This is so what this formula means is that you should, so it's an exponential, so you should expand that, and the expansion precisely means that you will consider first 1 power of L, so you first break, you first do go to a genus 1 boundary, codimension 1 boundary, then you break again, and so on, and there is a finite number of breakings you can do. Well, okay. If you sit down a few minutes and try to compute that integral, you will see that eventually you will have to compute integrals in M04 or in M03, on M11, and so on. So this is quite standard in the notation with intersection numbers, and this is typically the type of forms that Mumford was writing. Okay. Now let me do an example of application of this. And this is the topological vertex. So now let me choose another curve. So let me choose the curve. We want to be the dual, the mirror of so this is the mirror of C3. And let me add a framing, and by multiplying by y to the power f. So this curve is the mirror curve of C3. Now let me go to exponential variables. Let me write that x equals exponential minus x and y equals exponential minus y. And way to parameterize this equation is take z belongs to C something, and x, so the log, minus log of big X is minus log z plus f log of 1 minus z. Y equals minus log of 1 minus z. And now take b z1 z2 equals dz1 dz2 over z1 minus z2 to the square. So this is my curve. So in fact, to be well defined, you need to remove probably the segment 0,1, CP1. Okay. Well, first of all, it may look like B. So the way I've written it, you could think that B has no BKL terms. It looks exactly, it seems that it's just that without extra terms. But this is not true, because here I was using the local coordinate that was square root of x. Now I'm not anymore using the coordinate square root of x, I'm using another coordinate. So the z that I write here is not the square root of x. So you have to make a kind of change of variable. So the change of variable that you should use, let me call it zeta instead of z. Zeta should be square root of x minus the position of a branch of the ramification point. Let me call it x of L. So then B is not dz1, d zeta 1, d zeta 2 over d zeta 1 minus zeta 2 to a square. So now there is a full expansion. So we are in that case. Let me redo the same computation as before about the times here. Let me redo the same computation as before. In fact, it will not be R, but I think 0 to 1. And it will not be, sorry, it's not z squared, now it's x, where x is given by this formula. So this is integral from 0 to 1 of, so e to the minus ux make z to the power u times 1 minus z to the power minus fu. So this is just exponential minus ux times eta, and eta is log, eta will be, so sorry, here in this, eta is y dx. Well, before going further, let me integrate by parts. So we have y dx, and this is just by integration by part. This is integral from 0 to 1 of e to the minus ux dy. Just integration by parts. And this is more convenient. So this is 1 over u, integral from 0 to 1, z to the u, 1 minus z to the power minus fu. And what is dy? Dy is 1 over, so dy is z over z minus 1. Okay? And you recognize the Euler beta function. And this is 1 over u, gamma of u plus 1, gamma of minus fu, over gamma of u plus 1 minus fu. In fact, again, you need to multiply by 2u to the power 3 halves, square root of pi, and so on. And after you do that, you realize that your exponential minus sum of t hat k u to the minus k should be, well, let me write it this way, gamma hat of u plus 1, gamma hat of minus fu over gamma hat of u of 1 minus f times u, where gamma hat is basically the part of gamma where I have removed the leading term in the Stirling approximation. So gamma hat of u is gamma of u divided by u to the power u and exponential minus u on square root of 2 pi on square root of u. Okay. So now gamma hat of u has a 1 over u expansion. Basically, gamma hat of u is the part of gamma u which has a 1 over u expansion. And so this is the final result that we get for our t case. No, this is not exactly the final result. Because gamma hat of u has, as I said, has a 1 over u expansion. This 1 over u expansion, it is well known. It's sum over k, b2k over 2k minus 2, u to the 1 minus 2k. And b2k is the b2k equals the Bernoulli numbers. So it is the steering formula. So basically, it's the steering formula. So what have we found? We have found that the class that will appear in our computation here will be exponential sum over k, b2k over 2k minus 2. Sorry, maybe it's a 2k minus 1, sorry. 2k minus 1, kappa 2k minus 1, plus 1 over f to the 1 minus 2k kappa 2k minus 1, minus f minus 1 to the power of 1 minus 2k, kappa 2k minus 1. Plus, okay, plus, so in the exponential, we have plus this sum over 1/2 of this sum over delta, sum over k on L, this L star, so this BKLs, L star delta of psi k of tau k tau L. And in fact, I will tell you what the BKLs are. In fact, they are also Bernoulli numbers. Well, it's just a result. It's a very similar computation to that one. So you just basically redo the same computation with the Laplace transform of B, and you will end up with also Bernoulli numbers. Okay, it's a little bit tricky, but it's not. It's just that. So I will tell you what is the. So let me introduce that the following quantity: lambda alpha equals exponential sum of k d2k 2k minus 1 kappa k plus 1/2 of sum of delta, sorry, alpha to the 1 minus 2k, delta sum over k plus L, sorry, sum over g equals 0 to k minus 1, I think, tau k minus 1 minus j, and minus psi 1 to a k minus psi n to a k. Let's call that class this way, and basically this is the one that will appear as the result of this theorem. So the result of this theorem is that you will basically get that. Well, I've included in the exponential some of the terms coming from here, which corresponds to making a small change of basis on the side D's. I've included them just because this is the famous Mumford formula for the Hodge class. Which is sum over k of alpha to the minus k ck of the Hodge bundle. maybe there is a -1 to k. To power k. Okay. But okay. Basically, what we have observed is that starting from the spectral curve, just computing the Laplace expansion, we get the times, and the times are those that create this class, and we recognize that this class is exactly a Mumford class. So what we have in the end, using this theorem, we have proved that the omega gns defined by the topological recursion, omega gn of the topological recursion are, well, okay, let me concentrate on omega g0 to go faster. Omega g0 is some prefactor times the integral over mgn bar of, and we have the lambda, the Hodge class of 1, the Hodge class of, sorry, -1, the Hodge class of f, and the Hodge class of 1 minus f. Basically, well, times some prefactor that, okay, contains some trivial powers of f and f minus 1. This is the famous Marinova formula. And this is the Gromov-Litani variant. Of C3. So, by using all this chain, what we have proved is that if you start from that spectral curve, which is the mirror of C3, so you start from the mirror of C3, you just apply the theorem. For that, you have to compute Laplace transforms, and what you get is that omega g0 are the Gromov-Litani invariants of C3. So it's a consequence of that theorem. Now, the more difficult case is when you have, so I'm almost done. So I started 10 minutes after, so we finish in a few minutes.
Yeah, you can.
But so the third case is the case where you have several ramification points. So when you have several ramification points, for each a, you shall use the local variable square root of pi of z minus pi of a. Okay, it's a local variable in the neighborhood of a ramification point. Again, you do expansions for eta, and call the coefficients t a k's. Do the expansion of b, call the coefficient b a k b l's. So you expand one of the, so meaning that you expand one of the variable in the neighborhood of a ramification point A, and the other variable in the neighborhood of a ramification point B, called AK, BIK, BL, the coefficients in the Taylor expansion. Also define the, okay, also define those forms, psi AD, okay, and the theorem is now that one. Okay, the theorem now is the sum over, it contains the sum over graphs, and these graphs are precisely the dual graphs of degenerations of Riemann surfaces of genus G. So these graphs are precisely the degenerations of surfaces of genus G with n boundaries. So the graphs where each time you have another point, you replace it by an edge and so on. And you have a product over edges of the coefficient b's. And for the outgoing legs, so for the marked points, you have the psi ADs, as usual. And the value of the vertices are these times of integrals over the mgns sitting at the vertices. So the vertices of the dual graph are some vertices of the dual graph are some smooth, correspond to smooth Riemann surfaces of some genus GV and NV. Okay, and basically this is the same formula as before. So in fact, when there is only one nodal point, when there is only one ramification point, the sum of graphs I was rewriting it as an exponential quadratic, but because these are finite graphs. So basically, in the case where there is only one ramification point, this is exactly the same formula as before, or in other words, the exponential with sum of degeneracies that I was writing before is exactly the sum of graphs. Okay, so now when you apply this theorem to more complicated spectral curves, and in particular the mirror of some more complicated Calabi-Yau threefold. So let me go to no. Okay, let me take the. Okay, I will show you. Not belong. Okay, let me take two examples of Calabi-Yau manifolds. Let me take two examples of Calabi-Yau threefolds. One is the resolved conifold. It's a subset of C4 given by, so you have, okay, it will be hard to illustrate, but take the subset of C to the power 4, where with this relation between the moduli of x1, x2, x4, and so on, and modulo this equivalence relation among the angles. This is the resolved conifold. Okay? The way you write it as a toric graph. So first, so it corresponds to this picture. Plot in R plus to the cube. What are the possible values of modulus of x1 to the square, modulus of x2 to the square, modulus of x3 to the square? In fact, only the part contained between the red lines. So somehow, everything that is beyond that face is excluded. It cannot be obtained because it would correspond to a modulus of x4 negative. So it cannot be obtained. So, so basically there is a polyhedra that can be obtained, and the edges of that polyhedra is what is called the toric graph. In fact, you can look what are the normals to the faces, and when you write the normals to the faces in coordinates, so let's say that alpha j, beta j, gamma j is the coordinate of the vector normal to the face, to the j face. And when you plot the points alpha j, beta j's, sorry. Well, okay. When you plot the points alpha j's, beta j's in the plane, they are integer points, and they make a graph, and you plot a line. So remember, each point is the coordinate of the normal to a face. So each point corresponds to a face of the polyhedra, and you draw a line if two faces are adjacent. And that makes the blue graph. And this defines, and this is how you will define the, this blue graph will be the Newton's polygon of the mirror. So let me write the mirror corresponding to that. So we have 4 blue points that correspond to 1 plus x plus y plus e to the minus t tilde xy equals 0. Let's do again a framing. So change x to x times y to the power f. And so here it's y to the f plus 1. Okay. Work with work out all what I said about the Gromov. So sorry, compute the omega g ends of that curve. So you have to do several Laplace transforms and so on, and you get a sum of graphs. on the sum of graph is very similar to the localization graphs of the Gromov-Witten theory. I will not have time to go further, but the idea is that so from topological recursion you get a sum of graphs. From localization of Gromov-Witten theory you get a sum of graphs. And this is not exactly the same graphs, not with exactly the same values, but then by doing just combinatorics, you can rearrange one set into the others, and in the end, you can prove that they have the same value. And in the end, you can prove that this works for every toric Calabi of three folds. What you compute from the topological recursion using the mirror is the same as the Gromov-Witten invariance in the A model. So in the end, this is a statement of mirror symmetry. So topological recursion is the B side, Gromov-Witten theory is the A side, and they compute the same thing, and this is a theorem for all toric Calabi-Yau orbifolds. Okay, thank you for your attention.
Questions? Everything is clear.
Yes, sorry, may I ask? So for the resolved conical now, we can take like more complicated Lagrangian coming from more complicated and it also is
I don't know. I would say probably yes, but
maybe we will know next week.
yeah, maybe.
Other questions? Let's thank Bertrand again. And we'll start in 20 minutes.